4 different ramp angles. The angle of the ramp will be referred to as theta ramp. And this ramp angle is the smallest angle that the incline makes with horizontal ground. All right, so since all of these objects are identical, they'll feel the same forces of gravity. And I want to draw their forces of gravity just as vectors here. They all point directly downward, and they all have the same magnitude. What we want to do next is analyze other forces that are acting on the ball. And there's really only one place that it can come from. It comes from the ramp itself. This is going to be the normal force. Now, we had already seen that in some situations when a ball is on level ground, the normal force is equal and opposite to the weight of the ball. So there's equilibrium. But what happens in free fall? In free fall, we know that there would be no normal force. And in fact, even in this situation where the ball is very close to the surface of a ramp here, the surface doesn't exert a normal force on that ball. Like, for example, imagine the ball was just next to the surface, not actually touching it, and in free fall. Then since there wouldn't be any contact, there wouldn't be a normal force. But what happens in these two cases in between? Well, that is the subject of this video. We like to align the x and y axis for a ramp so that the x is pointing down the ramp and the y is pointing perpendicular to the ramp. So let me go ahead and draw what that would look like. This would be our positive x direction. And this would be our positive y direction. Now, what we're going to do next is we're going to take that force of gravity and we're going to resolve it into its perpendicular components that are in line with the x and y axis. So what does this entail? I'll do it over here on the side so that you can see how it works. We want to trace our arrowhead of FG to the x and y axes. This requires making a perpendicular with the axis. And it'll create a rectangle. Then what we do is we form the y component of FG and the x component of FG. This one's going to be called FGX because it's in line with the x-axis. It's parallel to it. And this one's going to be called FGY. These force components turn out to be very useful for analyzing motion on ramps and forces on ramps. Now, the reason that I drew the FGX and FGY in dashes is because I don't want to ever confuse the fact that they are components of this real force, Fg. I don't want to indicate or imply that the ball is feeling 3 forces here. It's only feeling one force, and the black dashed vectors are the components of that force. Okay, now that we have that, we can finally draw the normal force. And how big is the normal force? The normal force has to be perpendicular to the surface of the ramp. So it's going to be directed this way. But how large should it be? Well, one fact we know is that the ball, when it rolls down the ramp, it doesn't sink into the ramp, and it doesn't fly off the ramp either. It never loses contact with the ramp's surface. What that means is that the forces perpendicular to its motion are balanced. And so what we want is we want our normal force to be exactly as long as the FGY component. That way they're balanced in the y dimension. Okay. Now, what would happen if we did this same process on a 60-degree ramp rather than a 30-degree ramp? Well, let's try that one down here. Okay, so we want to trace our arrowhead to the x and y axes, making a rectangle out of the traces. Now let's create our components. And label them. As you can see, the lengths of the vectors are now a little different than they were before. The FGY is not as large as it was before, and the FGX is actually larger. I still want to have balance in the y dimension, though, so I draw my normal force. And it's not nearly as large as it had been on a ramp with a lower angle. I'll draw the components over here as well. What this shows is that the steeper the ramp is, the smaller the normal force will be. The lower the ramp angle, the larger the normal force will be. And also, it gives us an explanation of why balls have different accelerations on different ramps. So which ramp angle has the largest acceleration? That would be the free fall ramp. In free fall, you can achieve an acceleration of 9.8 meters per second squared. But we also know that when we're on a ramp that is level, then we would have an acceleration of 0. Now the acceleration goes down as the ramp becomes more level. We want to create formulas for the force which pulls us down the ramp. Now which force here is unbalanced? That would actually be this, the force of gravity in the x direction. This is the unbalanced force. And it is also on the ball. And this one would also be a net force. Okay, so how do we find a formula for this net force down a ramp? It comes from the geometry of the situation. So let's check out this ramp here. This ramp was making a 30-degree angle with the horizontal. Now by similar triangles here in geometry, this would also be a 30-degree angle, and so would this. And as you can see here, we've got a couple right triangles. So we should be able to use trig relationships to find a formula for FGX and FGY. So let's use the sine of the angle. We see that the sine of the theta would be the opposite, which is FGX, over the hypotenuse, which is FG. Okay, now, and I'll put absolute value around that so we don't have to deal with any negatives in this situation. And then if we rearrange it, we find that the net force on the ball will be equal to FGX, which is equal to FG sine theta. It's also worth noting, though, that if we were to set up a cosine theta, we would be able to solve for FGY. And sometimes that formula is useful as well. So we would see that FGY is going to be equal to FG cos theta. These formulas turn out to be very useful. Now what if we want the acceleration of the ball down the ramp? We know that it's 9.8 meters per second squared in free fall, and it's 0 for level ground, but say we want to find the acceleration down one of these other ramps. We can use Newton's second law for this. And if we do a little substitution here, okay, so we'll get FG sine theta over m. And if you recall the weight formula, Fg equals mg, then this term here, then this factor here, Fg over m, is nothing more than g. So this is going to be a formula for the acceleration down a ramp. It has to do with g, the acceleration in free fall, and also the theta of the ramp. So when the theta is 0, then the sine of theta is also 0, and you don't have any acceleration on level ground. But if the theta is 90, then sine of 90 would be 1, and you have free fall acceleration.